This physics lesson, we are going to study capacitor networks, whereby we're going to look at capacitors in series and in parallel, and we see how to go about the questions. The figure below shows 4 capacitors connected to a battery, 12 volts. So a battery of 12 volts is connected here, such that we have a 5 microfarad capacitor, a 2 microfarad capacitor, 8 microfarad, and 3.2 microfarad capacitor. Then we are taught to calculate effective capacitance. So for us to get effective capacitance, I can do the part 1 here. For us to get effective capacitance, we should look at the connection. And these two are in series. And when they are in series, we add the reciprocals. And because they are just 2, we can have the products divided by the sum. Therefore, we will have 2 times 8. Then we divide with 2 plus 8. This gives us 16 over 10, which makes it 1.6 microfarads. So we have 1.6 microfarads instead of these 2 capacitors. Now the 1.6 microfarad capacitor and the 3.2 microfarad capacitor are in parallel. And when capacitors are in parallel, to get effective capacitance, we add them directly, such that now the 1.6 we have gotten from above, and the 3.2, since they are in parallel, we can just add them directly. This will give us 4.8 microfarads. So for these and these, we have 4 microfarad capacitor. Now after that, the 4.8 microfarad capacitor is in series with the 5 microfarad capacitor. Therefore, we add the products. 5 times 4.8, and we divide with 5 plus 4.8, which gives us 24 out of 9.8, and the total capacitance in this connection will be 2.449 microfarads, which is going to be 2.449 times 10 power negative 6 farads, the SI units. So instead of microfarads, we can have them as farads by dividing with 1,000,000. So that is the total capacitance, or the effective capacitance in the connection. The next is charge on the 3.2 microfarad capacitor, the charge flowing through this capacitor. The charge flowing here can be calculated when we first of all determine the charge in the whole system. Now that we have effective capacitance and we have the voltage, we can get charge in the system. So effective charge is given by CV, capacitance times voltage, 2.449 times 10 power negative 6 multiplied by 12, and this gives us, when we multiply this, we will get 2.939 times 10 power negative 5 coulombs. So the effective charge in this system is 2.939 times 10 negative 5 coulombs. So that is the effective charge in the whole system. If that is the effective charge in the whole system, what we should know is that in the 5 microfarad capacitor, the total charge passes here. Total charge proceeds here of 2.9 times 10 power negative 5, because the charge from here has to pass uniformly in every component in series until the charge reaches here and gets redistributed in the 2, depending on the voltage. So we can get voltage in the 5 microfarad capacitor. Voltage in the 5 microfarad capacitor. By getting this, we will have solved first of all number 3 here before we get to number 2. So we can start with number 3, whereby in the 5 microfarad capacitor, because charge is given by CV, then to get V, we need to get Q out of C, such that we can have a charge of which is the total here, 2.939, and we divide, okay, times 10 power negative 5, and we divide it with the capacitance there, which is 5.0 times 10 power negative 6 coulombs, microfarads. To make them farads, because it is already 5, we make it times 10 power negative 6 to be in SI units. So when we divide this, we'll get 5.8, sorry, 78 volts. Therefore, the voltage in the 5 microfarad is 5.878 volts. Now, after getting the voltage there, we can have the voltage which proceeds here, and from the totals of 12, we can subtract 5.878 to give us 6.122. So voltage which proceeds now, the voltage which proceeds to both the 3.2 and to this other branch here. So when voltage now, the balance, when the balance comes here, which is a voltage in the 3.2, which is 12 minus the voltage at the 5 microfarad, which is 5.878, we're getting 6.122 volts. So the 6.122 volts is the one which now redistributes itself equally to this part and also to this part, such that now at the 3 microfarad capacitor, 0.2, Roman 2 now, this was Roman 3. This was Roman 3 sorted first. So Roman 2, to get charge, then we need C and V, and we got both. The capacitance is 3.2. We multiply by 10 power negative 6, multiplied by a voltage of 5.878. And this gives us a charge of 1.881 times 10 power negative 5 coulombs. So this is the charge which passes in the 3.2 microfarad capacitor. The other question which we are supposed to calculate is the energy stored. For us to get energy stored, we should first of all know that for us to get energy, then we need half C multiplied by energy stored. The energy stored is given by half charge times voltage, because the graph of charge and voltage, charge and voltage is a smooth line or a straight line through the origin, which means for us to get the charge stored, then we need the area under the graph, and the area under the graph gives us total charge. So this means that we can get energy stored by half Q times V, which means instead of half Q times V, we know that this energy can be given by half. Instead of Q, we can use CV, and using CV, and we already have V here, then we can use half C and V squared. So V can be squared, and we have C instead of the first formula here. So we can use capacitance and the voltage that goes there, So now we can check the first formula here. Okay, the formulas can be three. We are saying energy can also be given by half CV squared, and again energy can be given by, instead of V, we can use Q out of C. So we can say half Q, and instead of V, we say Q out of C, such that half Q squared over C, half Q squared over C can also give us the same component here. Therefore, let me prefer the first formula, where energy is given by half QV, such that we can use half, and Q is the charge flowing in these. So we know that the charge flowing in the whole system is 2.939, and now we know the portion which goes through the 3.2, which means we can get the balance, so that we know the charge that flows now in these two capacitors. So when we have 2.939 and we subtract 1.881, we are getting 1.0. So the charge is 1.058 times 10 power negative 5, and we multiply this with the voltage. So when we multiply this with voltage, remember, voltage should get to this one uniformly, such that the voltage of 5.878 which came here, or which passed in 5, the balance we said is 6.122 which came here and redistributed itself uniformly. So which means the voltage of the same 6.122 comes to this capacitor. So we will use 6.122, and this one is going to give us the energy stored, whereby we multiply half 1.058 multiplied by 6.122. So this gives us 3.2385 times 10 power negative 5 joules of energy. So this will be the energy stored in that capacitor. Thank you for following. Subscribe and share this link.